Okay, now we come to lecture 8 in this series. So far, we have spoken only about single channels in the steady state. But real life, that's rather rare. Synapses don't operate anywhere near equilibrium. They operate when a pulsive agonist comes from the presynaptic nerve. So in this one, we're going to deal with the non-equilibrium state. Turns out to be not too complicated. This lecture will be a sort of introduction, really, to this particular paper in 1997 by Anton Molushkin, among others. This is about what single channels are predicted to look like after a pulse of agonist concentration. In principle, the same results or very analogous results would apply after a step in voltage, though we have never done that ourselves. For a rather simpler account, you can look in the blue book, Sackman and Nayer's single channel recording. Chapter 18 includes some numerical examples of, as well as the particular bits of algebra which we shall go on to now. We'll use this by now rather familiar mechanism as an example, binding of two agonists sequentially to a Schutz channel and opening when it's either monoliganded or when it's biliganded. It's too simple to account for any known channel, but its simplicity is a virtue for exploratory purposes, explanation purposes. Again, we partition the matrix into open states, these two, and into shut states, those two. And in fact, we'll divide the shut states into long-lived shut states, such as the vacant receptor, if you're working at a very low agonist concentration, which are between bursts of openings, and the shorter shut times, which are within bursts of openings. Though in this case, it'll turn out that we need to define the B and C subsets a little differently from before. So there's the Q matrix for this mechanism, and it's partitioned into the states are partitioned into set A, set B, and set C. We'll come to how they're defined precisely in a few minutes. The top left-hand submatrix, for example, that describing transitions among open states, is that. We'll also define, as before, as a set which is, we can call burst states, E, and that's either the open states or the shut times within a burst states. So it's the union of A and B. So if we partition the Q matrix in that way, we get QEE here. This contains all of the states that it can be within a burst, and QCC here, the states, only this one in this case, which are the entry into which defines the end of a burst. So with that preliminary, let's consider single channels after a jump. We'll consider first a simple case of a jump from zero agonist concentration up to a finite concentration. Why do I say a jump? Because it's a basic assumption of everything we do that the Q matrix is constant, doesn't vary with time. That's where the exponential solutions come from. So if the concentration changes, the concentration appears in the Q matrix, the concentration mustn't change. Well, of course, if you jump in concentration, it does change, but it has to change instantaneously from one constant value, in this case 0, to another constant value, a finite, the finite concentration after the jump. Of course, you can't get a jump that is actually instantaneous, but you can sometimes do it to a sufficiently good approximation. It turns out that if the channel doesn't show correlations, these were dealt with in the last lecture, then everything is very simple. All the opening times, shut times, and bursts are exactly as already derived for the steady state case. The only exception to that is the first latency distribution. And the first latency is the time from the moment the agonist is applied to the start of the first opening. So it's a distribution of shut times. In the steady state, the distribution of all openings, we have seen many times now, is given by this expression. Phi naught is a row vector. Phi O, I should say, is a row vector which describes the occupancies of the various open states at the beginning of the opening. And if we swap open and shut states, we get the distribution of shut times as this. We now have an initial vector which contains the occupancies of the shut states, and that initial vector you can just write as in this way. It's the opening initial vector times GAF, which describes the transitions from open to shut, regardless of how long they take. So to get the distribution of the first latency, all we have to do is to substitute in the normal equilibrium expression the appropriate initial vector for the shut time, the fraction of all channels in each shut state at time equals 0. So for that 5-state mechanism we put up to begin with, they'll all be in the unoccupied state, at state phi. So phi f at 0 will be 0, 0, 1. That's state 3, 4, and 5, the shut states. So the first latency probability density function is simply the open time distribution, except that instead of starting off with the equilibrium vector, we start off with this one, 0, 0, 1. So it's actually simpler than before. So that we're considering this sort of jump at the moment, a jump from 0 up to a finite level. And we can notice that once we're within the shut states, the expression for the distribution is the same whether we're in the steady state or not. What differs is the initial vector, the entry probabilities, the relative probability of starting in each of the shut states, for example. And so what varies are not the time constants, but the areas of the distribution. We might also notice that in that short account, we didn't take into account the possibility that the channel might be open at t equals 0, but in the absence of spontaneous openings, that's going to be very low. So let's now deal with the more general case where there are correlations between open and shut times. Again, it turns out that all we have to do is get the initial vector right. The first latency distribution had an initial vector given by that. So after the first latency, we get an opening, if any openings occur. So the initial vector at the start of the first opening is the initial vector at time 0 times the transition probabilities for opening, regardless of how long it takes. That's for the first opening after the jump occurs. For the rth opening after a jump occurs, we've got, if it's the rth opening, it's described by the transitions between open to shut and shut to open r minus 1 times. And this gives you the initial vector for the rth opening. So apart from using that, nothing else needs to be done. For example, the mean length of the rth opening is given by that expression. It's exactly the equilibrium expression, except that we use the appropriate initial vector. And if there are correlations, that means that the first, second, third opening after a jump could, in practice, could be predicted to have different distributions with different means. In practice, we haven't been able to detect this, it must be said, but that's what it means in principle. Of course, eventually, as time goes to infinity after the jump, the correlation decays and they approach their steady state value. So here is our example mechanism again. This one shows correlations as we showed in the last lecture. One way of looking at why that's the case, because we have to delete two states to separate the open and shut times. We could delete, for example, state 3 and 4. That means that the connectivity is 2, so correlations will occur with lag as a single geometric distribution. As we showed last time, that's the same as saying that the rank of GAF, GFA is 2. GAF is defined in that way. QA is non-singular, so it has full rank KA. The rank of GAF is usually then the same as the rank of QAF. Partitioning the Q matrix again into open and shut. QFA we see is this. QAF is that subsection, and it's the rank of these that controls the presence of correlations. But now we come to an unfortunate complication, which caused some puzzlement at first. Notice that the Q matrix has entries in which involve the concentration of agonist. So this is the jump from 0 to a finite concentration that we've dealt with so far. But if you want to jump to 0 concentration, a complication arises. For example, the shut section of the Q matrix, QFF, written as a function of agonist concentration here. Then XA is the agonist concentration, which occurs here and here and here. So we can write QFF as a function of the agonist concentration. So this is QFF, which applies when the agonist concentration is XA, but here the concentration falls in principle instantaneously to 0, and QFF therefore has this form. The bottom row is all zeros now, and that row of zeros means that QFF is singular, so the usual expression for calculating GFA, say, just won't work, because this bit of it is singular, and therefore that inverse doesn't exist. So what the heck are we going to do about this? Well, this was solved in Molushkin. And we can solve it by noticing that when the concentration is jumped from a finite value to 0 at t equals 0, there are 3 possibilities. Firstly, the channel may be open at t equals 0, because we were in a finite concentration. If the t equals 0 occurs while the channel is opening, that will be the case. Eventually, of course, it will shut, but it may then reopen several times before the agonist finally dissociates and the activation comes to an end. It's also possible that the channel was shut at t equals 0, but in a shut state, the can open without having to bind more agonists, because the agonist concentration is 0, so you can't bind any agonist, but it might reopen anyway. Of course, it may not actually reopen, but it can do. And the third possibility is the channel was shut at t equals 0, but it was in a shut state that can't open in the absence of agonist. In this case, the channel is trapped and can never open after t equals 0. So the channel was open at t equals 0, meaning it's in state 1 or 2. At t equals 0, the channel was shut. In set B, that means in this case, it was in state 3 or 4. If it was in 4, then of course it can open without binding any agonist. If it was in 3, it can also open, though only to the monoliganded state at 0 concentration. So set B is 3 or 4. And if it was in set C, that's only state 5 in this case, then of course it can never reopen again. So just as when we discussed burst analysis, the states are divided into sets A and B and C, but now B and C are defined slightly differently. This explains why. This is a step to 0 concentration. There's that line represents 0 time. So what can happen, the 3 cases I've described before, the channel was open at t equals 0. It will eventually shut, but may reopen several times. So in these diagrams of the sort we've seen before, the upper trace shows which set the channel is in, the lower trace shows what we actually observe. The red bits represent open states. These are openings are shown as downward deflections here. If the channel was shut at t equals 0, but in a shut state that can open without having to bind agonist, then we would see something like that. It was in a B state initially. It may then reopen with even with zero agonist concentration, and may open and shut several times before eventually the agonist dissociates and gets trapped in the C state. And this is what we actually observe. This time from the time the concentration was reduced to 0 to the time of the first opening is the first latency. Or in general, the time from the step in agonist concentration to the first opening is the first latency. Of course, if the channel was in a B state at 0 time, it doesn't have to reopen. It may just go straight to the C states without opening, in which case you don't see anything. And if the channel was in a C state at 0 time, it can never open, so you just see nothing. Now, these possibilities can be put together without using the QFF matrix, which is singular at 0 concentration. After a jump to 0 concentration, there will either be no openings at all, or a finite number of openings, which we can describe as one channel activation. The fraction of jumps which give no openings will be no openings if the channel was in a C state at 0 time, or it was in a B state and goes straight to C without reopening. So the fraction of all channels at a null probability of 0 openings after a jump is the sum of the occupancies in the C states. Now these are the occupancies of the B states multiplied by the transition probabilities for going from B to C, regardless of how long it takes, again summed up over the C states. Remember that post-multiplying by this unit column vector adds up the elements in this preceding row vector. So the fraction of all jumps that produce at least one opening is 1 minus that. Probability of R equal to or greater than 1 opening after the jump, 1 minus that. And we can easily show that this is given by the intuitive expression. This is the sum of all of the occupancies in the open state at t equals 0. These represent the channels that were open at time 0, the channels that were in a B state, but then, regardless of how long it takes, produce an opening. So the distribution of the number of openings after a jump, given that at least one of them occurs, is given by this. The probability of R openings after a jump is given by this. That's the initial vector, probability that R is bigger than 1, in other words. And this is the absolutely standard steady state result that we had before. So all that changes is the initial vector. So now let's consider the distribution of the length of an activation from the start of the first opening to the end of the last opening. We can write down the Laplace transform of this fairly easily, as in the case of the burst length distribution. It's very similar. The inversion is quite tricky. This is another one that I got and was quite pleased about. This you may recognize is the same as the steady state burst length distribution, except the steady state initial vector is replaced by a different one. And this turns out to be the initial vector as for the previous slide, conditioned on there being at least one opening. So again, we see that all that differs from the steady state is the initial vector. All the rest is the same. So this is the length of the activation, the burst of openings that occurs after a pulse of agonist. Measured from the start of the first opening. What happens if, rather than measuring it from the start of the first opening, we get the distribution of the length of the activation measured starting from time equals 0. So it includes the first latency as well as the length of the subsequent burst of openings. But it turns out that this involves just the same exponential of the burst section of the Q matrix, the EE section, but rather than taking the AA subsection of this matrix, we take the EA subsection. So it's like the normal burst length distribution, but we use the EA section of this KE by KE matrix, not the AA section, because in this case, the integral can start in any burst state. That one I was very pleased with, so elegant. But notice that the time constants of these distributions depend entirely on this exponential bit. They are the time constants for the observed distributions will be the eigenvalue, or 1 over the eigenvalues of minus QEE, and they're exactly the same in both of these expressions. All that differs is the initial vectors. So we expect that we will see the time constant, same time constants for all these distributions, but just with different areas for the different distributions. These expressions all had a sort of end of burst vector, which if we go back to the burst length distribution, we can see can be written in various ways. This is the end of a burst because it measures the probabilities of going from A to C. That clearly should be UC there, because otherwise it wouldn't add up. Sorry about that. Equivalently, we can write it this way, or we can write it that way is also to be UC. This last form we can find in the 1982 paper in the appendix. It is directly analogous to the 1 minus p in the equivalent scalar case, as we've already seen. Notice that these end of burst vectors all have the dimensions of reciprocal time because of this minus QAA. The Q matrix contains transition rates, all are in all have the dimensions of reciprocal time, and the rest of the expressions are all dimensionless. So a thing that puzzled me for quite a while was the relationship between the length of a burst of opening as a single activation of the channel and the macroscopic time constant. It was clear from our 1977 paper onwards that what had previously been known as an open time was actually a burst length. And just as we expect open times to be what controls the time constant for the decay of a synaptic current, we now expect burst lengths to do that. But there's a problem in that interpretation, because the probability density function for the distribution of burst lengths, as we've seen repeatedly, is that. So it has KE time constants that are the reciprocals of the eigenvalues of minus QE in the standard way. But the macroscopic current depends on the time course of the number of open channels, and that is given by this. The time course of any sort of macroscopic current will in general have a different number of time constants that are found from the k-1 non-zero eigenvalues of minus q because of this e to the qt term. So in principle, the burst length distribution has a different number of eigenvalues which are defined differently from that in the macroscopic current. This puzzled me for quite a while. But the Maleschkin paper solved that. If we want to write now in terms of current, not occupancy, we can write it this way. This is the macroscopic current, P naught e to the qt. And to convert it to current, we may need to multiply by the total number of channels we're recording from, the voltage, the driving force, and the single channel conductances, which we can write. Here, in this final column vector, which multiplies by the single channel conductances, in the A states, the open states, the rest of the single channel conductances are zero. That's in general, but in the special case of a jump to zero concentration, it turns out that we can write the expression this way. Rather than the whole of qt, it involves only the EE subsection of qt. In the particular 5-state example we've been using, these happen to be the same, but in general that won't be the case. These are the size of these various things. This current is scalar. This is the initial vector, 1 by KE. That's, of course, is KE by KA, because we're only using the EA subsection of it, and the conductances are equal in number to the number of open states. Now, the point is that the burst length distribution also has the same set of time constants, the eigenvalues of minus QEE. So, in fact, the macroscopic current has exactly the same number of time constants, the same values of the time constants as the burst length distribution, as long as the bursts are measured at very low concentration, so that the concentration is approximately zero. So we've seen that the time constants for observable events depend only on the value of Q at the time of measurement. But the amplitudes or areas, if they're distributions, depend also on the initial condition or the entry probabilities, the state of the system at the start of the event. So we expect that the following quantities will all have the same time constants, only the relative areas, and hence the overall mean will vary. The time constants, the time course of relaxation after a jump to zero concentration. The burst length distribution for bursts recorded at very low agonist concentrations. And the time course of the average of such bursts or activations when they're excised and aligned on their first opening. Or the length of a single channel activation that follows a jump to zero concentration, measured from the start of the first opening to the last end of the last opening, so the latency is excluded, or the length of the activation that follows a jump to zero concentration from t equals 0 to the last end of the last opening, so that we include the latency. All these 5 things ought to have the same set of time constants. And this we observed in 1992. Alistair Gibb did some nice experiments which showed this phenomenon we hadn't done the theory fully by that time. And these were native NMDA receptors. Because they were native, we aren't sure what the subunit composition was, but they look very much like NR1, NR2A. And we observed the correlation of the sort that I mentioned in the last lecture rather clearly in this case. This is the open times, the mean open time for openings that are are next to shut times in a certain range around here, plotted against the mean of that shut time range. So we see that next to short shut times, we see long openings, and next to long shut times, we see shorter openings. We can see this with other receptors too, though it's particularly clear in the case of NMDA receptors. But we also observed that in this case, the open times could be fitted with the sum of 3 exponential components with time constants, tau slow, tau middle, and tau fast, and that these time constants were the same regardless of the adjacent shut time. What differed between these various open times was the areas of the components. So the area of the fast component this one, increased, and the area of the slow component, this one, decreased. And this is why the distribution gets faster. The open times get shorter, in other words, next to the long openings compared with next to the long shuttings, compared with their length next to the short shuttings. We can go on to another example at a time when we understood better these distributions. These were done on recombinant receptors, NR1A, NR2A, they call GluN1 and GluN2, I think now. And we looked at steady state activations. David Wiley looked at steady state activations with low agonist concentrations. So with the NR2A subunit, we got things like this. This is a fairly compressed time scale. And we can see that they occur in bursts. The horizontal line above each of these things marks where we think the bursts of channels, single activations occur. With the 2D subunit, we get much longer activations. They're a bit difficult to define, but again, the horizontal line marks where we think each activation of the channel begins and ends. If we look at the length of these activations, they were called superclusters in this particular paper, but it doesn't really matter what we call them. They're the lengths of these activations marked by the horizontal lines. We find we can fit 6 exponential components to them. Notice the wonderful resolution you get with single channel measurements. You could never fit 6 exponentials to a macroscopic curve, but you can fit them with reasonable consistency to the length of these channel activations. We see with the 2A subunit, the longest component is 200 milliseconds, though the area for these 40 milliseconds and 4 milliseconds is a bit higher. With the NR2D subunit, the activations are much longer, with the slowest 2 time constants being 1.4 seconds, that's 31% of the area, and 5.2 seconds, which is 23% of the area. So the NR2D channel is very slow indeed, as is fairly well known. These are some steady state activations by low glutamate concentration for the 2D type channel, and they've been aligned on their first openings, and the average of these is pretty damn noisy. You couldn't fit a lot to them, but what we can say is they're compatible with our prediction, because we can fit these aligned activations with the time constants fixed at the values found from the fit of the activation length distribution in the last slide. So we had 1.4 seconds and 5.2 seconds from that distribution of the length of the activations, and we can fit this average with those time constants if we fix them during the fit. Of course, it's only the amplitudes are not easily predicted, because they what depend on the opening probability, the entry probabilities, the initial vectors. But the same time constants will fit. So that doesn't show that our rule was true, that the time constants are the same for the two different ways of measuring it, but it is compatible with that postulate at least. What about the jumps? Well, the jumps are done with a very short jump of glutamate concentration from 0 up to 1 millimolar and then back to 0. This is how we normally do concentration jumps. This length of this may be only 1 millisecond. It's commonly the case. So that T pulse may be only 1 millisecond. How do we predict the response to that? Well, the general formula for state occupancies, this row vector contains the occupancies at time t, was that. We've written the Q as a function of agonist concentration in this case. That is the same old Q. So at the beginning of this pulse, the initial vector is P naught for this step. That's in general, since it starts from 0 concentration, it'll be in the resting state. We can then calculate from this general expression the occupancies at 1 millisecond. At the end of the pulse, there'll be this, the initial vector times the Q matrix for 1 millimolar times the length of the pulse, and these will be the initial vector for the step back to 0. So for occupancies at time t after the end of the pulse, the initial vector will be that, and the Q matrix will be that for 0 concentration after the end of the pulse. So let's look at the average response to jumps at time 0. And these are fitted with the time constants fixed at the values obtained from the activation length distribution. Notice that this is about 30 seconds long. The pulse of agonist concentration which elicited this was only 1 millisecond long, and it produces these time constants of, well, again, it's fitted with time constants that were obtained from the activation length distribution, 1.4 seconds, 5.2 seconds for the slowest two time constants. And we notice that, so these are now average responses to jumps of 1 millimolar glutamate for 1 millisecond, and they're fitted with the time constants, the same ones as before, the ones obtained from the burst or activation length. There's two slow time constants of 1.4 seconds and 5.2 seconds. Notice that this also predicts the rising phase of here, and the time constants from the activation length distributions, the next fastest ones are 4.7 milliseconds and 66 milliseconds, and these now appear with the opposite sign because these now define the rising phase of this current, but they still fit. again, we can't fit to a signal as noisy as this all of these exponential components, but we can show that the average here is compatible with having the same time constants as the distribution of the length of activations. Now, finally, we come to the miracle patch. This was recorded by David Wiley on the 16th of October, 1996. So it's just over 25 years old now. It was never published because it could never be repeated. But it was just a wonderful patch which shows the phenomena I've been talking about more clearly than up to now, perhaps. These are 5-second sweeps showing the response of a 1 millisecond pulse to 1 millimolar glutamate. So this is the concentration here. That tiny blip there is where the concentration was raised to 1 millisecond to 1 millimolar glutamate. And these are the results of some of the pulses. This one, you see, the first openings occur a long time after the pulse. In other cases, the openings occur almost immediately after the pulse. And here's a sweep in which there were no openings at all, just as predicted before. And David recorded 456 consecutive sweeps like this. The concentration jumps done with the piezoelectric theta glass method, of course, to get jumps this fast. And in all 456 sweeps, a double amplitude opening was never seen, so it's almost certain that we were recording from only one channel. That's a really difficult bit, which only happens by luck. And that was the average of the 456. In fact, it was described roughly by a time constant of 250 milliseconds. This is for the NR2A type channel. If we blow up those, so that was 250 millisecond calibration. This is a 50 millisecond calibration, so these are 1 second sweeps rather than 5 second sweeps. The dashed line shows the moment when the pulse was applied, and we can see there the first latency was around 50 milliseconds in that particular case, but it's very variable. If we look at the distribution of the 456 first latencies, they look like this. They go through a peak that suggests that there's shut states that intervene, probably more than one, between the binding and the opening of the channel. And a specific model for this was predicted by Stephanie Shorger in 2005. We might come on to that in the last lecture when we're discussing fits. The average of these first latencies was about 20 milliseconds. So the channel, this is the faster of the NMDA channels, is pretty sluggish in opening. We give it a 1 millisecond pulse. On an average, we have to wait for 20 milliseconds before the channel opens. In 96, we didn't have a complete model for the mechanism. That came much later, so we couldn't interpret this in detail other than to note how sluggish the channels are at opening. And once they've opened, how complex the length of the single activations are. Here we have many, many openings triggered by a 1 millisecond exposure. And here again, we have many, many openings triggered by that 1 millisecond pulse of agonist. Here we got none at all. This is the situation we've been describing. And given the mechanism, we can predict this to see whether that mechanism describes these phenomena sufficiently accurately. Okay, that's it for jumps. Notice that we're still in the business of predicting from a model and rate constants what we expect to see. The next time we'll get on to a topic which is essential to do the fitting, which is our ultimate aim. We'll talk about the effects of time interval omission, the fact that you can't see openings and shuttings below a certain length. And the correction for this turns out to be crucial, not least for glycine receptors. And that's what we'll deal with in the next talk.